What is up, guys? It's Dan from sagemathtutoring.com. I am at the beach. Hopefully there's not too much of a breeze here, and you might hear some seagulls in the background, but shouldn't be too much of a problem. Anyway, here is a review sheet for the final of a 7th grade student that I'm working with, and he had circled some of the problems that he had questions about, so I'm going to make a nice video that sort of explains some of the concepts and how to do these problems. So let's begin right now. We've got number 6 right here. Name the polynomial by its degree and number of terms. X squared plus 9x minus 14. All right, so the first thing to take note of is how many terms you have. And there are 3 terms, so that makes it a trinomial. And the fact that there's an exponent of 2 means that it's a quadratic trinomial. All right, so that would be lowercase letter b. Now, I'm going to kind of draw a little breakdown for my students to help my students understand how to properly classify polynomials real quick. So I'm going to do that right now. So right now we're going to focus on degree first. So when you're classifying polynomials, the degree talks about the largest exponent that's present in the polynomial. So for example, if you have something with a degree of 0, that means it's like, imagine having like 5x to the 0 power. Well, honestly, that just equals 5. And the reason for that is because 0, the exponent of 0 turns x into a 1, so it's really 5 times 1 equals 5. And what we would call that is a constant. That's what we call that. When we have a degree of 1, an example of that would be something like 4x plus 5. Now notice how we're focusing only on degree here, which means we're focusing only on the exponents. There happen to be 2 terms here, but the highest, exponent present is this 1. That's kind of like hovering above the x right there. So anytime you have a degree of 1, one way of classifying the polynomial is to call that a linear polynomial. If you have a degree of 2, that means the highest exponent present is 2, so something like 3x squared minus 2x plus 7. Again, focusing only on degree, the highest exponent present is 2, and we call that a quadratic. When the degree is 3, which means the highest exponent is 3, we refer to that as, one moment, so let's call this 30x to the 3rd. And notice how this only has 1 term, but again, focusing on degree, therefore focusing on the highest exponent present, we call that a cubic polynomial. When you have a degree of 4, it looks like the teacher wants you to call that a 4th degree, blah, 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 blah. So we're just going to call that a 4th degree. Let's get an example here. So imagine you had 47x to the 4th minus 2. Well, that would be, quote unquote, 4th degree. Okay. And, with regards to fancy ways of memorizing this stuff, it's not always obvious, unfortunately. For example, with the constant, that's kind of just a matter of memorizing it. There is a reason for calling it a constant, because this is always 5 no matter what. There's no variable attached to it, so this value just kind of stays the same no matter what, so it's constantly 5. Whereas this term right here might change. If x is 1, then the whole term is 4. If x is 2, then the whole term is 8, and so on. So this term is not a constant, whereas this term is. With regards to the linear, I think my student is probably somewhat familiar with the whole y equals mx plus b stuff. And by now my student knows that that's definitely a line. This kind of looks like a line. Anytime you have that exponent of 1, if you were to graph that polynomial, it would turn out to be a line. That's why they call it linear. All right, line. Quadratic, I'm not exactly sure the best way to memorize that, other than, I'm going to use my artistic skills here. In the human anatomy, you have a person who All right, we're gonna analyze the human leg. Okay. Imagine a superhero leg with the calf and the thigh, muscular thigh, and so on. And usually the quads are the thigh muscle. And if you look at like a person who's like really jacked, their quads, there's usually, at least close to the knee, there's only 2 pieces of muscle that really stand out. All right. That's a really odd, strange way of remembering quadratic and associating the word quadratic with 2. All right, but sometimes the weirder the better, to be honest, so we're just going to leave that there. With regards to cubic, best way to remember that, in my opinion, is the fact that a cube totally has 3 dimensions. You have length, you have width, and you have height. And it so happens that these all equal each other, but the real important thing to focus on is the fact that there's 3 dimensions there. So there's 3. 4th degree is probably the most obvious out of all these. I'm going to assume that the teacher wants exponents of 5 to be a 5th degree trinomial and so on. So anyway, this is an example of classifying polynomials by degree. It looks like the teacher is definitely going to want my student to classify the polynomials also by the number of terms. So let's kind of get a sense of that real quick. So yeah, imagine you were dealing with the number of terms and you want to classify polynomials by the number of terms. Well, we're not going to put 0 here because, if you have 0 terms, then you just don't have anything, right? So we're not going to worry about that. Now, if you have 1 term, for example, something like 3x to the 4th, we call that a monomial, and probably easy to remember due to the word mono, which means 1. If you have 2 terms, for example, something like this, then that is a binomial. A lot of people have an association with this word bi as being 2. Bicycle has 2 wheels. The binary system has 0s and 1s only, that you're considering. So binomial for that. If you have a polynomial that has 3 terms, for example, 4x squared minus x plus 2, well, as my student I'm sure would guess, that is a trinomial. And then finally, if you're dealing with 4 terms, and an example would be something like 5x to the 5th minus 2x to the 3rd minus 2x plus 1, and right there, that is an x I ran out of room. A lot of teachers will just refer to that as a polynomial. All right, so at that stage in the game, it's a polynomial. So the teacher is going to want you to sort of combine these insights. For example, if you had something like 3x squared minus 7x plus 2, well, that right there, when you look at the degree, you can see clearly it's a quadratic. But when you look at the number of terms, it has 3 terms and therefore it's a trinomial. So you are dealing with a quadratic trinomial. A quadratic trinomial. I'll just write quad, T-R-I-N, for trinomial. All right, so that's that. If you had something like this, where it's like 4x to the 3rd, well, looking at the degree, it's a degree of 3, so it is a cubic. As far as how many terms it has 1 term, so that's a monomial. So therefore, monomial. So it's a cubic monomial. All right. So start by focusing on the degree, actually. That's what I would advise. And then go to the number of terms. Are you going to have to get a sense of these and sort of memorize these? Unfortunately, yes. You're going to have to sort of memorize these names here. All right. Hopefully that helps. Once again, x squared plus 9x minus 14. That is a quadratic trinomial. All right, looking at this one now. So let's see, simplify all that shenanigans. Right. Well, when it comes to these like fraction things where you have a string of a bunch of variables with crazy exponents and so on, you can This one's an interesting one. So here's what I would advise. All right, there's faster ways of doing this, but the sort of most reliable way that will work every single time is the following. Basically, you have to make sure that like is stacked over like. So this is already written in such a way that like is stacked over like, which is great. You're also going to want to take note of any, if you have an exponent of 1 hovering above any particular variable. Now, for my student at home is very bright, so I believe that my student at home totally could tell that, to be honest, he could just cancel these z's, and to be honest, he could just cancel these as well, because anytime you have the same number over itself, it just cancels out, basically. Now, that's totally true. Nonetheless, I do think it's going to be smart to go about this in a systematic way. And what I mean by that is to do this, where basically you realize that this x shenanigans here, you have x to the something over x to the something. Well, what do you do when you have the same variable, with exponents, one on top of the other? You keep the variable right here, and you subtract the bottom from the top. So that's literally this. Subtracting the bottom exponent from the top exponent. Now, only by coincidence are the exponents the same, but that's what you do. You subtract the bottom exponent from the top. Then I would focus purely on the y's, and in this case it's going to be y, keeping the base, and then it's going to be 5 minus 7. We're subtracting the bottom exponent from the top. There it is. Similarly with the z's, even though we know, yes, we could cancel it, nonetheless, let's rely on the systematic approach. That's going to be keeping the base and subtracting the bottom from the top. Now, when you do that, let's analyze what happens on the next line. We have x to the what? Well, we have -5 minus a -5. That's really -5 plus 5, which is really a 0. Over here, we have y to the -2. Over here, we have z to the 0. Now, as my student knows, x to the 0 is just 1, z to the 0 is just 1. So at the end of the day, we really just kind of have y to the -2. And we know that that could hypothetically be rewritten as that, 1 over y squared. So once again, you could use your sort of, brains and realize, okay, cancel, and then take it from there. Or you could rely on the systematic approach that will definitely work every single time, as long as you are careful. Now, my student did not circle this one. I nonetheless want to address it. In the interest of time, all I'm going to say is that if you have a big clunky fraction, or really any fraction to be honest, let's say we had something like this, and it was raised to the -3. Anytime you have a negative exponent, like hovering above a fraction, first thing I would do to just save myself massive confusion, and this might be straying a little bit from what the teacher says, but the first thing I would do is I would recognize that anytime you have a negative exponent above a fraction, you could, if you wanted to, and I think you do want to, change that to a positive and flip the fraction that's inside, and then take things from there. Because nobody wants to think about this thing hovering on the outside, so you can kind of do this quick move to just get it all over with in a way, and then take things from there. All right. Now, when it comes to this, clearly what that would mean for us is to have a +2 on the outside, and let's really get clear here. We're going to have 20 x to the -4, y to the 5th, w -5, x to the negative 9, y to the negative 20, and w to the 6th. All right, now I'm not going to harp on this one because my student did not circle it, but what I would say is this is going to be a lot easier of a situation because this 2, it's better to have this be positive. I would take things from there. Now, what do I mean by take things from there? What I mean is simplify all this stuff in pretty much the exact same way that we did up here. Simplify it. And then you're going to come up with something at the end of that that is a little simpler, and you're still going to have a 2 on the outside. And I can kind of tell right now what it's going to be. In fact, I'll just kind of do it. This would end up being a negative 4 up top. We would have an x to the 5th up top. We would have a y to the 25th. We would have, let's see, just a w to the 5th down below. All right, so that's what would happen. And for my student at home, just know that this 2, when it's on the outside, it gets applied to everything. All right. In fact, that's 2 laws that I did not really go over today with them. This equals that. So in other words, if you have a product and an exponent on the outside, you can apply it to both terms. Similarly, if you have a fraction, well, you could also apply this to the top and the bottom. So that becomes a to the x over b to the x. So this gets applied to literally everything. It gets applied to the top and bottom due to this law, and it gets applied to the entirety of the product due to this law. So let's just get this over with. Negative 4 squared, what's that? Well, that's 16. So it's going to be 16. X to the 5th raised to another power of 2. Well, you keep the base, multiply the exponents. That's going to be x to the 10. Y to the 25th raised to the exponent of 2. Well, what do? You keep the base, you multiply the exponents because we're raising a power to a power. So that becomes y to the 50. Now remember, we're applying this exponent of 2 down below. So that would be w to the 5th raised to the 2nd power. That's going to be w to the 10th. Now there's always a chance I made a careless mistake. If you believe I made a careless mistake, just make a comment below and we'll, I'll definitely correct it for sure. But yeah, that's what it should be. So I guess I will do the problem. I can't help myself once I get started. All right, so that's how you want to handle that stuff. I did write down a list of laws for my student, but here are some additional laws to take into account when it comes to exponents. Hopefully that makes sense. Let's move on to the next one. Okay, classic, find the area of the shaded region. So sometimes these are referred to as donut problems, and they're actually not that bad. When it comes to problems like these, it's going to be the area of the larger thing, I'll call it A sub L for larger, minus the area of the smaller thing. So really that's all there is to it. So let's find the area of the larger thing. Well, the area of the larger thing is going to be length times width. So the area of the larger thing is going to be, I'll call it 5x times 3x plus 2. Boom, right? Done, right? Well, not done, but it's a start. Then the area of the smaller thing, we're going to subtract. Well, the area of the smaller thing is, length times width or width times length, doesn't matter what order. That's going to be 5x minus 2 times x. So that is 5x minus 2 times x. All right, now for my student at home, I can already foresee what is going to be a challenge that will trip up the average students. And that is the fact that we're subtracting this entire thing over here. So I want my student on the test to be very much on the lookout for subtracting a whole gobbledygook mess of string of addition, subtraction, blah, blah, blah. There's a big mess over here, and we're subtracting the whole thing. Now, when you're subtracting the whole thing, you might want to just get it over with and stick brackets around it, because that will serve as a reminder that I'm not just subtracting the first term that we come up with here. I'm literally subtracting the whole darn thing. Now that we've reminded ourselves of that, let's focus here. Bottom line is, this is one term, this is two terms. You could totally distribute that 5x in there. And by doing so, you will get 15x squared plus 10x. And we're going to subtract a whole thing of something over here. I'm preserving the green brackets. Now let's figure out what's inside here. Well, this x could totally distribute here and here. So we end up with 5x squared minus 2x. Now you're going to see the purpose of the green brackets. We are subtracting the whole thing, and the reality is we have a secretly we have a -1 right there that's being multiplied by the whole thing. That's the reality of what's happening here. I know we don't typically think of it that way, but for these problems, it actually does help you to think of it that way, for problems where you're subtracting a whole product like this, okay? So we have a -1, so we're going to distribute a -1 here and there, and when you multiply anything by -1, what does it do? It changes the sign. So we're going to have 15x squared plus 10x. Now, inside the green, it's just a positive 5x. Now it's going to be a negative 5x squared plus 2x. Had we not put the brackets around it, a lot of students would make the mistake of just calling this negative 5x squared, and they would have left this negative 2x alone. But remember, we're distributing the -1 here and there, therefore we have to change this sign. Now we have like terms here and here. That becomes a 10x squared. And we, of course, have like terms here and here. That becomes a 12x. And since we don't know what x is, that is as far as we can go with that one. All right, so that's how you do that. All right, so this is a classic annoying parabola problem. Let's see, they say y equals x squared minus 3x minus 10. Right, well, this is the standard form of a parabola as opposed to the vertex form. There's like other ways of writing this equation in a way that might even actually make it easier to graph, believe it or not, but the teacher is throwing my student to the wolves by giving standard form. The good news is the teacher is sort of walking you through the process of, you know, when given standard form, what do you want to do? Well, let's find the vertex first. Now, I actually think finding the axis of symmetry, in a way, comes first. Now, the axis of symmetry is this, where it's like, it's going to be x equals negative b over 2a. Now, what do I mean by that? Well, when the quadratic function is written in standard form, this is the case. So a in this case is this invisible 1 that's in front of here, b is this -3, and c is this -10. So what I'm going to do actually is write down off to the side reminders. So we have a equals 1, b equals -3, c equals -10, and again, axis of symmetry, negative b over 2a. So in this case, axis of symmetry equals negative something over 2 times something else. Notice my parentheses again. And now I'm going to worry about filling them in. Negative what? Negative b. What's b? Well, b is -3. -3. The purpose of me doing the parentheses is to make sure I'm very clear it's a negative. Down here we have a. That's just 1. And what does that equal? That equals +3 over 2, which is a very annoying number. A very annoying number. But nonetheless, it's correct. And why did I do the axis of symmetry first? Well, the reason I did that is because the axis of symmetry is actually the x-coordinate of the vertex anyway. But let's be clear on what sort of the final answer is when, you know, you present to the teacher the axis of symmetry. What your teacher wants to see is maybe, you know, some of this work right? But then we'll kind of do a little divider here. The sort of final quote-unquote answer is x equals, literally, 3 over 2. Now that, believe it or not, is the equation of a line. It's equation of a vertical line called the axis of symmetry. So what I'm going to do is I'm going to draw the axis of symmetry right now. 3/2 is 1.5. So that is a vertical line that absolutely passes through 1.5. Totally goes through the whole thing, all the way up forever. Dotted line, yay. Now, how do you find the vertex? Well, we already know that the vertex is on the axis of symmetry. So the vertex is 3/2 comma y. Now, we don't know what y is, and we're going to go on a mission to find it. Now, what do I mean by the vertex is on the axis of symmetry? Well, what I mean is the vertex is on the axis of symmetry. Okay, so maybe the parabola looks like this, and the vertex is necessarily on the axis of symmetry. That's just part of, like, you know, the definition of a parabola. All right, somewhere on there. Okay, so let's look here. So basically, how are you going to find that? Well, it's not that hard conceptually. I mean, you just take 3/2 and you plug it into the equation. So that's really just a matter of taking the equation and finding out what y equals when x is 3/2. So that becomes something squared minus 3 times something minus 10. Well, what is that something? That something is 3/2, which I'm going to put in there. So we'll do a little divider. 3/2 goes inside each of these, right? And when we work it out, that becomes 9 over 4 minus 9 over 2 minus 10. If you wanted to work that out further, a good common denominator would be 4, so we're going to leave this alone. This is going to become 18 over 4, and that's going to become 40 over 4. So I'll write that down in case my student's confused by what the heck I just said. It's going to become that, and this is going to become that. My student can always pause the video to make sure he understands that this is the same as that. All right, and then working that out would give us, let's see, 9 minus 18 is -9. Minus 40 is -49, so that's like -49 over 4, which is some weird number. I don't know, like negative 12 point something. Yeah, -12 point something. So nonetheless, that is the answer, actually. So we now know what y is. It's -49 over 4. If I was the teacher, I would not have a problem with the student literally just writing that, -49 over 4. All right, and again, that's like -12 point something, so that's like down here or something. And by the way, I find it to be, it's a little bit annoying because the teacher did not give us enough room to graph that vertex, but it's, you know, down here somewhere. All right, and I am double checking with my graphing calculator, and it does indeed look like we are correct. Okay, we are correct so far. So this graph happens to be not large enough, but nonetheless, we know it's down here somewhere. Let's draw a little yellow thing that's like right around there. So roots and or x-intercepts. So your teacher's kind enough to be like the roots or x-intercepts. Basically, this is your teacher's way of saying the roots are the x-intercepts. It's really just the same thing. Two ways of describing the same thing. Well, how do you find that? Well, finding the x-intercepts, all you have to do is set y equal to 0. So that's going to be 0 equals the equation x squared minus 3x minus 10. X squared minus 3x minus 10. And then my student at home should know that you could totally either use the quadratic formula, which by the way will work always, or you could factor it. So if possible, you might want to factor it. Looks like it is possible. We have 2 and 5 as factors of 10, and that makes me think of 3. So this would end up becoming, I'll do this as the next line, 0 equals 2 little parenthesis things. We have x, we have x. We're definitely going to have a 5, we're definitely going to have a 2. This is going to be the positive, this is going to be the negative, because we want the larger number to be negative to plunge this into the negatives. All right. Based off of my student's understanding today, I believe that he will understand what I meant by that. So we have x equals positive 5 and negative 2. So in other words, this parabola totally crosses the x-axis at 5 and negative 2. That is really useful. All right, that is really useful to know. So we're going to put a thing here at negative 5, and we're going to put, oh wait, no, was it positive 5? What am I doing? Positive 5. I knew something was wrong with that. Positive 5 right there, and negative 2. Which totally makes sense even visually, right? And then you're like, whoa, boom, boom. And by the way, let's get very, very clear. This vertex right here is 3 over 2. I know the yellow is annoying. 49 over 4. Let's just deal with it for now. That's the vertex. And the reason I say that is because soon the teacher is going to want to know the range, and that's going to come into play soon. Domain. Okay, well, the domain basically means all the x values that are on the graph, right? Now the bottom line is this clearly goes up forever. I mean, that's just obvious, right? These are little arrows here. But one thing that might be less obvious is that it also goes out forever. Okay, so what that means is, since it goes out forever, that means literally all the x values are on the graph somewhere. Like, for example, negative 500 million. Well, that's on the graph somewhere. It just happens to be like up really high, you know, on the parabola somewhere. But negative 500 million is totally on the parabola somewhere as an x coordinate, right? So in other words, the domain is the set of all x coordinates that happen to be on the parabola, right? So different teachers have different ways of talking about this part too. I find that probably most teachers use this infinity notation, where it's like negative infinity to positive infinity. So in other words, all the x values infinitely to the left into negative infinity, and all the x values infinitely to the right, positive infinity. The range is a different story. The range is the set of all y coordinates that happen to be on this graph. Now, you might notice that the y coordinate of negative 20 is totally not on the graph. Imagine we counted down to the negative 20. That wouldn't be on the graph, right? So what's like the smallest y coordinates on the graph? Well, it's the y coordinates of the vertex. So that's that should be negative 49 over 2. Negative 49 over 2. Right? It's negative 49 over 2. So literally, this is negative 49 over 2 to positive infinity. All right? Now, to be clear, negative 49 over 2 is right here. That's literally the smallest y value on the graph. And then all the other y values above that, also known as infinity, are included on the graph. Now, you may notice the brackets next to negative 49 over 2. You put brackets to communicate to the reader that negative 49 over 2 is actually included in that set. Okay? Now, you might ask, well, why didn't we put brackets around infinity? Infinity is included in the set too. And I will just say that this is a decision that mathematicians decided. They're just like, let's put parentheses around infinity, because infinity is weird. It's included, but it's not included. We don't really understand. It goes on forever, so can we really say it's included? I don't really know. So just know you always put in parentheses around infinity, whereas any number, you know, this is an actual number right here, any numbers that are included in the set get a bracket. Hopefully that makes sense, and that's how you do that. All right, looking at this shenanigans now, we got this one right here. Well, it's probably the case that there's some cancellation that can take place. Otherwise, the teacher wouldn't be asking us to simplify it. Now, you don't want to be cocky and just assume that there must be a cancellation. Let's just say Most of the time there will be. Occasionally, your teacher's going to test your ability to know that there can't be a cancellation sometimes, right? But that's pretty rare. So, nonetheless, the top and the bottom can be factored. The top can be factored into x, 12, and 1. We have positive, positive. No question about it, right? What are the factors of 12 that when you add them would give you 13? Well, positive 12 and positive 1 are factors of 12. And if you added them, you would get positive 13. Done, right? There it is. Now, based on my students' performance, I don't feel the need to harp on that too much. X squared minus 144, that is most definitely the difference between two squares. So that's really something squared minus something else squared. Well, what is that something else? 12, right? So this is clearly x squared, and this is 12 squared. So that could totally factor into the pattern, the very famous pattern that says we could factor that into x minus 12, x plus 12. In case you need a reminder, the following is true. A squared minus b squared equals a minus b times a plus b. Depending on your textbook, you might have a plus b times a minus b, but either way, it's something like that. The order doesn't matter because multiplication is such that the order does not matter. Cancellations right there, and then we are done. X plus 1 over x minus 12. That is finally the answer. I'm going to assume the teacher does not care about restrictions. Yeah, I'm going to assume the teacher doesn't care about restrictions. It's the case that x can't equal negative 12 or positive 12 because then it would be undefined. Some teachers insist that you make note of that and then you simplify it. So for my student at home, just be aware, ask yourself, has my teacher ever asked me to find restrictions? And if so, you need to write down. If your teacher cares about you mentioning restrictions, you have to write down that x cannot equal these two numbers because if x was a positive 12, this would be 0. If x was a negative 12, this would be 0. And you're not allowed to have undefined on the bottom. So you have to actually square that away right away, like in the beginning. You have to actually do that in the beginning, not based off of your answer. You have to do it in the beginning because notice how we canceled these, right? It's still true that x is not allowed to be negative 12, even though we canceled these. All right, so for my student at home, if it's the case your teacher does not care about restrictions, you are in luck. That means the process is just as simple as this. Oh, look, restrictions. There you go. So seeing as how the teacher uses, talks about restrictions here, I'm going to assume we might need to mention those restrictions over there. Over here, we got 2 over blah, 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 blah. Well, what are the restrictions? Well, when they say list the restricted value of that, what they mean is set the denominator equal to 0 and find out what value of a would cause the denominator to be 0. So we're literally just working with the denominator right now. So it's 2a squared minus 4a. And we're forcing it to equal 0 temporarily. You could totally factor out a 2a, so that becomes a minus 2. And then you ask yourself, what value of a would cause this whole darn thing to be 0? Well, if that a was a 0, then it'd be 0 times whatever the heck that is, and that would be 0. So already, if we're going to solve this little miniature equation, a equals 0, that's one of the values. And also, if a was a positive 2, then this whole thing would be a 0, then it'd be a 0 times whatever the heck that is equals 0. So therefore, a is equal to 0 and 2. So these, even though we went off to the side and kind of did this little equation off to the side, these are the restrictions of this expression right here, right? These are the restrictions of this expression. So you could literally write, if you want to kiss your teacher's butt, you know what you could write? You'd be like, the restricted values are a equals 0 and a equals 2. All right, you could say a equals 0 and a equals 2. Now I would mention the restricted values. I would actually mention that. Restricted values are, right? Because what you don't want is your teacher thinking that you think that a equals 0 and 2. These are the restricted values. In fact, this is not even an equation, so we couldn't even say that anyway. All right, what is the lowest common denominator of that, right? In other words, if we were being asked to add these two fractions, what common denominator would we shoot for? Well, the common denominator, like the least common denominator of any two or more fractions, is always going to be the least common multiple of the denominator. So in other words, let's have a simpler case real quick. Imagine you have 5/7, and you were going to add that to like 2/3 or whatever. Well, the LCD of these is the least common multiple. Now, the least common multiple is some number that both of these numbers divide into, right? Now, I think my student at home probably would know that 21 is the least common multiple of 7 and 3, because 7 divides into 21, 3 divides into 21. Now, I do want to make clear it's only a coincidence that the least common multiple happens to be 3 times 7. It doesn't always work out that way. For example, if you had something like, 3/12 and you want to add that to 5, actually let's call this 3/12. Let's get a number that wouldn't reduce. 1/12 and you had 5/16. Well, it wouldn't be so simple anymore, because the least common multiple is not what you get when you multiply 12 times 16. One smart way of going about it is keep multiplying 16 times stuff until you find something that 12 goes into. All right, that's one way of doing it. So in other words, multiply 16 times 2, that gives you 32. And ask yourself, does 12 go into that? No. So multiply 16 times 3, that gives you 48. And ask yourself, does 12 go into that? The answer is yes. Therefore, ding, 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 that's the least common multiple. All right? Keep multiplying the larger number by stuff until you get something that 12 goes into. All right? Now, when it comes to these, what you have to do is just factor one or both of them, right? And then take things from there. So we're going to factor it first. We have 6 over, I know it's x, I know it's x, I know it's 1, I know it's 2, because that's all it could be. The question is, what's the sign? Well, it's positive 2, so they're either both positive or both negative. It's a negative, so that means they're both negative. So it's negative, negative. And then we have this 4 and x minus 2. Now, we could imagine we're trying to add these, even though it's not asking us to. But imagine we were, Well, what would be the common denominator that we could shoot for? Well, it's the least common multiple of these, of the denominators. What's the least common multiple of these? Well, actually, believe it or not, this is the least common multiple, right? Because this whole thing times 1 gives you itself, right? And x minus 2 times x minus 1 gives you this, right? So this is the least common multiple. All right? So when your teacher asks, what's the LCD, notice how the teacher's not asking you to add it. The teacher's not asking you to do any cancellations or simplify. All the teacher wants to know is, what is a number that both the bottom and the top divide into? Well, it so happens that that number is this denominator. The number is the first denominator. So the actual answer, written in blue, is the LCD, and maybe do a colon, and you can say x squared minus 3x plus 2. That actually is the least common denominator. Okay, hopefully that makes sense. Obviously, more practice with this would be good, and so on, right? And hopefully my student knows that, let's say I wanted to, make this fraction have that least common denominator. Well, as you know, you can't just multiply the bottom by x minus 1. You'd have to multiply the top by x minus 1, and then now you have the denominators the same, which is huge, but then you'd have to kind of multiply this and take things from there. All right, but notice how you're not even being asked to do any of that. All you want is the LCD. That's all you want. All right, looking at this thing, factor completely. All right, so we have D and all that. Yeah. Well, that's not even. That's divisible by 3. That's divisible by 3. Okay, so the first thing you want to do is you want to ask yourself, like, looking at the numbers, do just the numbers themselves have a GCF? Do the numbers themselves? And I'm already seeing Well, 6 goes into 24, 6 goes into 18. Do not believe 6 goes into this, though. Yeah, 6 doesn't go into that. 3 goes into everything. So, one thing's for sure. 3 times 8d squared plus something d minus 6. So 3 goes into 939. 3, 1, 3 times. Okay. Now this is not divisible by anything that I can think of here. Yeah, well, I had talked to my student before about finding like the magic number where like you take the first coefficient and multiply it by the constant in order to like factor quadratic trinomials that have a leading coefficient other than 1. And negative 48, so what you want to do is always that first, right? Because I guess what I'm looking for is 3 times something else, where, you know, maybe this would be 4D and this would be 2D and then there would be a number here, right? I want to see if this is possible. It might not be possible, but I want to see if it is possible. And the way to check is to do this. You just multiply the first coefficient times that constant. And then you ask yourself, are there any factors of negative 48 that when you add them together would give you a 313? And it's the case that the answer is no. Now, unfortunately, there's a lot of factors of 48, so you could like look at them all and analyze them. But what you'll see is that, you know, there's just no numbers that are like the absolute value of which are large enough that would even get us close to 313, like in the first place. So, you know, for example, you know, even 48 times 1, well, you know, like if it was like it was like a positive 48 plus a negative 1, well, that's just a 47. That's not even close to 313, right? And then there's things like, you know, 2 times 24, right? I mean, it doesn't bring us close. So, believe it or not, this is the answer. They say factor completely. That doesn't mean that it has to look like this. No, they mean, are there any GCFs going on? And if so, factor them out first. We did that. It's a 3. And then you could take a look and see if you could do the double sausage link deal, right? So even though it seems like, oh, it's a little uneasy, I feel a little incomplete here, that's actually it. All right, so that's the answer there. Okay, anything else on this page? Looks like no. Moving on. Then there is this one. All right, well, this looks like very scary, but it's not scary. The bottom line is, anytime you have a fraction and you're dividing it by another fraction, well, you keep the first thing, you flip the second thing, and you change it to multiplication. This principle that my student learned when he was very young still applies, because we just have a fraction divided by another fraction. So definitely, without question, first thing I would do is I would keep the first thing, right? I would change it to a multiplication problem, and I would flip the second thing. So a little dot, we're going to have 3x squared plus 18x minus 21, 9x cubed minus 18x squared. All right, so change locations because mosquitoes. So when it comes to this times this, you're going to want to factor the top and the bottom, factor the top and the bottom. All right, so we will focus first on this, and that's most definitely going to be x and x. We're going to have a 5 and a 2 for sure, and we're going to have plus minus. I trust my students to know how I got that. Down below, we're going to have a 7 and 1 because that's all you got when it comes to 7. and this is going to be negative. That's going to be positive. And then we're going to multiply that times the factored version of this numerator. Now, I really want to make sure my student realizes that before you embark on the journey of like factoring, there might be a temptation to even like, do 3 times negative 21 and get that magic number and all that. Really, the first question you need to ask yourself is, are there any GCFs like right away that I could factor out? And in this case, the answer is yes. You could totally factor out a 3. So really, you have, in fact, I'm going to write it up here above just to save some room. Bottom line is this could hypothetically be rewritten as 3 times x squared plus 6x minus 7, right? So I would much rather, do that. So it's like 3 times, and in fact, I'll just put green around these. It's really 3 times this whole thing, so it's going to be 3 times that whole thing, only factored now. So this becomes x. We have x. Once again, it's a 7. It's a 1. It is a positive 7 and a negative 1. All right, so this whole thing really just becomes that. All right, so always ask yourself, is there a GCF right out the gate that I can factor out? And the answer is yes, it's 3, so go ahead and do it. And then keep the 3 on the outside, minding its own business, factor that, and there you go. Similarly, there is most definitely a GCF going on down here. And in fact, I'm going to zoom in and write it in blue. This could be rewritten. Let's really zoom in. This could be rewritten as 9x squared times x minus 2. Now, if my student needs to pause the video to understand how this became that, then my student should do that. All right, but I'm actually going to keep this train moving. Bottom line is, I could most definitely represent this denominator as 9x squared times x minus 2. So that's what you want to do with these kinds of problems. Flip this one, change it to multiplication. We did that with the black here. Factor everything, and then look for cross cancellations now. Not cross multiplication, but cross cancellation. The x minus 2 cancels with that. These cancel. These cancel. We have an x plus 5 that doesn't cancel with anything. We have a 3 that does indeed cancel with the 9. So that 3 becomes a 1, and that becomes a 3. So once again, we have an x plus 5 that does not cancel with anything. And down below, we have a 3x squared that does not cancel with anything. So the final answer, when it comes to that problem, is x plus 5 all over 3x squared. Now again, there's always a chance I made a careless mistake, but I'm pretty sure I didn't, right? And yeah, you have to be careful with the cancellations and all that stuff. Make sure you're not leaving anything out, right? 3x squared down below. But that should be the answer right there. Okay, so are there any other problems on this page? Looks like no. Moving on to the next. All right, so this thing. So these are interesting. I like to think of the radical as a jail cell. All right. And for example, here's an example. Imagine I had 25 x squared y to the third. And the bottom line is, this is square root, so there's secretly a 2, like in that nook. They just don't write it, but there's actually like a 2. Each of these are prisoners inside the jail cell. And each of these prisoners are not allowed to leave unless they show a waiver, also known as an exponent of 2. they have to show an exponent that matches the index in order to get out of jail. So the question is, who gets out of jail and who's stuck behind? Well, 25 could hypothetically be rewritten as 5 squared. X squared is just x squared. This y to the third could hypothetically be rewritten as y squared times y. So anytime you have an odd exponent, you could always just shave off one and then form the even exponent right here. Now in this case, who gets out of jail? Well, clearly this 5 gets out of jail because he's showing a waiver of 2. This x gets out of jail. This x was always going to get out of jail based off of the initial, writing there. This y gets out of jail because this y is showing a waiver of 2. But this poor y is left behind. So who gets out of jail? 5x and y. So I'm literally going to write 5xy radical y. Done. Okay, if you want to simplify something like that, it turns into that. Okay? Now, occasionally, you might get a situation where, let's forget all this. Imagine we had something like, let's see, 50 x to the 6th. Well, the bottom line is, this 50 could really be seen as 2 times 25, right? So we're going to rewrite that as 2 times 25 times x to the 6th. But we're still not quite done. We're kind of all over the place here. But again, focusing on this, just bear with me. We already know that that's 5 squared. So we could write that. We could write, really what's happening is it's 2 times 5 squared, right? 5 squared. This x to the 6th, here's the move of the century. Anytime you have an even exponent, force it to have an exponent of 2 on the outside. So in other words, that could be rewritten as x to the 3rd with an exponent of 2 on the outside. Again, anytime you have an even exponent, force it to have an exponent of 2 on the outside. Now remember, a power raised to another power, you keep the base, multiply the exponents. So x to the 3rd raised to the 2nd power is x to the 6th power, right? So one more time, anytime you have an even exponent, force it to have an exponent of 2 on the outside, and ask yourself, 2 times what gives me 6? Well, in this case, it's 2 times 3 gives me 6. So this is x to the 3rd. Now, why did I write it like this? Well, to see who gets out of jail, right? This 50, I found a perfect square factor. I put it there, and I have my 2 over here. This is the largest perfect square factor of 50, in fact, which is what we want, 25. And why did I want a perfect square factor? So that I could turn it into 5 squared, right? So who gets out of jail? 5 gets out of jail, and x to the 3rd gets out of jail. So in yellow, who's showing a waiver of 2? That 5 is showing a waiver of 2, and this x to the 3rd is showing a waiver of 2. So they are the only 2 ones who get to go out of jail. So we have 5, x to the 3rd, radical 2. 2 is left over, right? So again, 5 was showing an exponent of 2, and x to the 3rd was showing an exponent of 2. So they got out of jail, leaving the 2 behind. So there's some more basic versions of this. Now, with something like this, you always want to ask yourself, okay, what is the greatest perfect square factor of 90? That is 16. Is that right? Yeah, 6 times 5 is 30. That's 16. So in other words, 90 is 5 times 16. 16 is a perfect square factor. So what I'm going to do is I'm going to rewrite everything, only in such a way that it's easy for me to see who gets out of jail. We have a 5. We have a 16. I'm just going to write it like that. Now let's begin the process of converting these. A to the third is really a squared times a. B to the fourth is really b squared raised to the second power. Right? Anytime you have an even exponent, force it to have an exponent of 2 on the outside. There it is. Anytime you have an odd exponent, in the same way that we did to this a to the third, shave off one right here and have the other one have an even exponent. So let's break this down a little bit more. This 5 is just a 5. We're going to represent 16 as 4 squared. We're going to represent this as a squared still. Now where I put the parentheses, it doesn't really matter. Right now, I'm just kind of using this line to clearly showcase which prisoners get out of jail. We have a b squared squared. We're going to have a c squared squared because of this 4, right? Force any even exponent to have a 2 on the outside. Just so happens we had to do it on this line instead of this line because we had to kind of do an intermediate step where we shaved off one, and now we're doing it here. We still have the c hanging out here. Now we're kind of perfectly set up to see who gets out of jail. Anything that we could have forced to have an exponent of 2, we did, right? That's the process. Force everything that can to have an exponent of 2. And that includes the number here by breaking it into factors. In this case, the largest perfect square factor was 16. Therefore, we could force that to have an exponent of 2. Okay? So, who gets out of jail? I'm going to wrap it up in yellow. This person gets out of jail. This gets out of jail. This gets out of jail. This gets out of jail. And everybody else stays in there. So we have a 4. We have an a. We have a b squared. We have a c squared. And who's left over? 5c. Done. Now, obviously, this is a process that requires practice to get used to. I'm hoping that this is enough for my students to just kind of understand, enough where he can put himself on the right track with whatever problem he gets on the test. So that is that one. Moving on to the next. All right, at a bakery, one customer pays that for 3 bagels and 4 muffins. Another pays that, right, and solve a system of equations to find out how much a bagel and how much a muffin cost. Right, so let's see. Right, okay. You got to ask yourself, what's the mystery? The mystery is how much a bagel costs and how much a muffin costs. So those are the variables that we're trying to find, okay? So we're going to say B equals cost of a bagel, and obviously M is going to be cost of a muffin, right? And as far as these kinds of problems go, we know that 3 times whatever the cost of a bagel is, 3 times B, plus 4 times whatever the heck the cost of a muffin is, well, that's going to total $5.67. We also know, based on the second situation, that 5 times whatever a bagel is, cost-wise, plus 3 times the cost of, one muffin, is going to total $6.70. And then the question is, all right, how do I, go ahead and solve these, right? Well, yeah, it's not obvious what would be a better route, substitution or elimination. I'm going to go with elimination because I'm worried that with substitution, like let's say I solve for m, I'm just kind of worried that it's going to result in a big ugly number with a denominator of 4 after dividing both sides by 4. So I want to do the elimination method here. And it's not obvious which variable to get rid of first, because the elimination means you want to eliminate one of the variables so you can just solve for the other one real quick. Let's just choose to get rid of the b's first. And the bottom line is, if I could turn this into a negative 15 and I could turn that into a positive 15, then they would cancel, right? Because you want to find like a good multiple of 5 and 3, preferably a least common multiple to work with, and one of them has to be negative and one of them has to be positive. Let's commit to the bottom being negative. It doesn't matter really. I could make the top negative and the bottom positive, but we're going to commit to the bottom being negative. So we're going to literally multiply the entire bottom thing by negative 3, because I know that when I do that, negative 3 times 5 is going to give me that negative 15 that I'm looking for. Similarly, I'm going to multiply the entire top by 5, because I know that when I multiply 5 times positive 3, I'm going to get a positive 15, and then these are going to be able to cancel. So let's bring everything over here, actually. We are going to have 15b plus 20m equals 28.35. And down here, we are going to have negative 15b plus, or rather minus 9m equals negative 20.1. So we've perfectly set it up so that these will cancel now. So when I add the entire top equation to the entire bottom equation, these cancel. And, we could even kind of denote the fact that we're adding them. So that's clearly 0 here. 20m minus 9, 11m. And when I subtract these, that's going to be 8.25. Dividing both sides by 11 gives me 75 cents. So that's a good sign. The fact that we ended up with like a reasonable decimal that represents monetary value. It would have been a little bit of a red flag if it was like 0.756 whatever, blah, 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 right? The fact that it's like 75 cents, very good sign. So we already found m. We're basically halfway there. So now all you have to do is just choose any one of these two. Doesn't matter which one. Just plug in 0.75 for m and then take it from there. I'm going to choose to use our green one. So that's going to be 5b plus 3 times 0.75 equals 6 point, I'll just call it 6.7. And that would be 5b plus 2.25 equals 6.7. Subtracting 2.25 from both sides would give me 4.45, and this is a B, not a 13. I'm trying to make it look nicer and actually make it look worse. And then we divide both sides by 5, and that gives me 5 into something 0, 8 and 9, right? Pretty sure that's right. Yeah, so 89 cents. So that should be the answer, unless, of course, I made a careless mistake. And I don't think I did, because those are reasonable monetary values. All right, so that's how you do that one. Moving on. All right, I do believe this is the last page. Let's see. Keith's dog weighs 80 pounds. Healthy weight for... This might be my favorite This might be my favorite typo of all time. Right here. All right, so a healthy weight for his dog would be less than 65 pounds. If Keith's dog can lose an average of 1.5 pounds per week on a certain diet, after how long will the dog reach a healthy weight? Yeah, so this is a linear equation. We're going to have to use a linear equation. I think maybe representing what happens graphically would be good. So for my student at home, imagine you want to use a graph, right? And, XY coordinate plane, like that's the x-axis, that's the y-axis. But you're trying to use it for like a real life situation. It's almost always the case that you want the x-axis to really be time. It's almost always the case that the x-axis is your time axis and the y-axis is like the other thing. In this case, it's weight, right, in pounds. So, great. And the bottom line is the dog starts at 80. That's the starting point, right? 80. That's where we began. And then over time, he's going to lose weight over time, right? And then at a certain point, he's going to reach 65, right? He's going to reach 65. Now, theoretically, in abstract mathematical universe land, this line could hypothetically go on forever, right? That doesn't quite make sense, but, in the real world, but in math land, this is a line, right? It goes on forever. So what we could do is we could kind of get a sense of, well, what's the equation of this line? What's the equation of this? Well, the equation is weight equals, I'm going to actually put the y-intercept first, because 80 is what you start with, right? That's the starting weight. And it's going to be a negative slope. It's going to be starting weight minus 1.5 pounds per week. So 1.5 pounds times t, right? We'll say that t is time in weeks. All right? So t represents time in weeks. W represents weight in pounds. Okay? Got to be careful with these variables, right? Because we could easily have used W for time because it's like weeks. How many weeks goes by? But then you have the weight equals 80 minus 1.5 W. Like, you don't want these variables to be the same. So I would stick with T for time always. Just know that the unit of time happens to be weeks in this particular, problem. So why did I do that? Why did I set up an equation? Well, I set up an equation because it will be easy now for me to find out how long will it take for the dog to reach a healthy weight. How long will it take for the dog to reach a healthy weight, aka 65 pounds or less, right? 65 pounds or less. So what you want to do is you want to force the weight to be 65 pounds. 65. And then you want to solve for t. You want to find out what t value corresponds with that. Well, we could keep the t over here. That's fine. Whatever. Let's subtract 80 from both sides. You therefore have negative 15 equals negative 1.5 t. And then dividing both sides by negative 1.5 would give you a positive 10. Now, your teacher might be a stickler for detail. The bottom line is, we just discovered that it will take 10 weeks for the dog to be exactly 65 pounds. But we need to make sure that we're clear that it's really this word after that's the key. Because the dog will be healthy when it's less than 65, not when the dog is exactly 65. The dog is healthy when it's less than 65. So at 10 weeks, this dog is exactly 65 pounds. So therefore, the answer to this problem is that the dog will be a healthy weight. The dog will, I'll just call it healthy, after 10 weeks. Not at 10 weeks, after 10 weeks. Now, this is just a sort of insurance policy that your teacher will sort of insist that you recognize that the dog is not healthy at 65, but the dog is healthy when it weighs less than 65. It will weigh less than 65 after 10 weeks. Because that's essentially what we discovered here, is that this moment where it hits 65 is 10, and then it dips below into healthy weight territory after 10. Okay. This is the healthy zone right here. So it's possible that my student totally gets it, and I do not need to get into this much detail, but that's how you do that one. All right. Now, student, friend at home, if you don't want to graph it, that's fine. But sometimes graphing the situation makes it easier to come up with the equation. You could have also written the equation as W equals negative 1.5t plus 80, where 80 is the y-intercept and negative 1.5 is the slope. That would have been fine as well. All right. And negative 1.5, this is not drawn to scale. It should be a steeper slope downward, but it's okay. For our purposes, all we need to really see is that it's decreasing. Okay. All right, so hopefully that is helpful, and I think that's it. So let me just double check one moment. Yeah, so this is the last page, so I do hope this was helpful, and for those of you watching, again, if I made any careless mistakes, don't think I did, but if I did, let me know. And for my student at home, good luck on the final coming up. It's a lot of information, definitely a lot of information, but you should have a much better understanding after watching this video. All right, so I will talk to you all later. Bye.